Talked a bit about rational numbers and irrational numbers yesterday. I guess the most common irrational number that we work with are surds. So let's just remind ourselves a bit about surds. They are, as I say, irrational. But basically, any number that includes a radical symbol is a surd. Well, includes a radical symbol and can't be worked out exactly. So like the square root of 4, that includes a radical symbol, but it's not a surd because you can work it out. Square root of 5, on the other hand, is a surd because you can't work it out. Now, radical symbol means not only square root, I mean a cube root is a surd as well, and the fourth root, they're all surds. Surd laws must be obeyed, otherwise the surd police come and lock you up and put you in surd jail. It's true. Okay, root A times root B. That's the rule that allows us to simplify surds, of course. It's the idea being we try and find the highest factor that is a perfect square, and then we can simplify the surd. Division, similar sort of thing. Doesn't matter whether you find the square root of the top or the bottom, or you do it all in one hit. And of course, if you square a square root, they're opposites, so they cancel, and you're left with A. So, there we go. Square root of 50. As I say, we're looking for the highest perfect square that goes into it, which of course in this one is 25. Not that you would write that line down, but of course that's what the rule is saying. Hey, I can break this up to be the square root of 25 times the square root of 2. So we rewrite it as 5 root 2. Talked about this earlier with algebra. I mean, that can still be simplified. And I guess the easier way of spotting it is when you look at it in index form. That would be x to the power of 3 on 2, which is an improper fraction. So therefore, the surd can be simplified. Using the idea of simplifying surds, we say, oh, well, I could rewrite that as the square root of x squared times the square root of x, which is x root x. But if we think of it with indices, we're saying, oh, x to the power of 1.5, x to the power of 1 times x to the power of half. So x root x. 5 on 4, not a big deal. I can't work out the top, but I can work out the bottom. So we just do that. We leave the top as the square root of 5. The bottom becomes 2. 20 on 9, again, I can work out the bottom, but the top can be simplified. So we have 2 root 5 on 3. All right. Surd arithmetic. Very similar to something else we wrote down at the start of the year. When we were talking about algebra, we said like terms can be added and subtracted, unlike terms cannot. And that's because surds are the same. Because we don't know what a surd is. A surd is an unknown, just like a pronumeral is an unknown. So the same rules apply. We can only add and subtract like surds. So when we get something like this, 4 root 3, yeah, okay, I don't know what the square root of 3 is, but I know if I've got 4 of them and I take away one of them, whatever it is, I've got 3 of them. So we can make that 3 root 3, and similar with the root 2s, but as far as adding them, can't do it because I don't know what root 3 is. I don't know what root 2 is, so how can I put them together if I don't know what they are? Becomes like a binomial product. First outside, inside last. Remember? The face. In this case, nothing simplifies down. Difference of 2 squares. Very common question in surds, because of course we use that in something else we'll see very shortly. And that is what we call conjugate surds. But conjugates are basically when you have the same expression, it's just the sign in the middle has changed. So we call those conjugates. That's 2 minus 1. Yes, it's 2 minus 1, not 4 minus 1. Common mistake. And that is just 1. And we can have perfect squares as well. So first one squared, twice the middle. Oh, twice the middle? Twice the product. And the last one squared, that tidies up to be 6 minus 4 root 2. Okay, the first part of our surd journey for today.